Welcome to the Solar Clips video series covering the basics of solar photovoltaics or solar PV. My name is Drew Chavone and I'm an extension specialist with the University of Maryland. In previous videos we considered the difference between DC and AC power as well as inverter sizing and the integration of DC and AC disconnects. You can review those videos for more information, but in today's video we're going to consider the integration of a solar inverter into this rather simple solar electric system, including any of the essential wiring that's needed. While we plan to avoid any overly technical aspects of the inverter installation, this video is still going to explore a high-level overview of the wiring and the connections that will help you develop an understanding and the skills required to install your own solar inverter.
To get started, let's review this simple battery integrated system that we developed in a previous video. For demonstration purposes, the system components were temporarily mounted to this wooden board. And if you recall, this particular setup consists of two separate 100-watt solar panels that are connected in parallel, and that parallel connection occurs within the combiner box, which houses some 30-amp fuses. Next, we have a 30-amp PWM charge controller connected to a 12-volt lead-acid battery, with the positive line passing through a 30-amp breaker. We also connected a small 12-volt DC motor to the charge controller, again passing this positive line through a 30-amp breaker. So as a quick overview, the solar panels collect energy from the sun, the charge controller regulates the energy coming from the solar panels, and then the battery stores that energy for later use. And as for the wiring of the system, we connected a negative black and a positive red cable between the charge controller and the battery, along with overcurrent protection in the form of a 30-amp circuit breaker on the positive line. This connection between the charge controller and the battery was completed prior to any connections being made to the solar array in order to avoid any possible damage to the charge controller. The stripped end of each battery cable was first fed into the corresponding terminal of the charge controller before tightening the terminal screws. The cable lugs on the opposing end of each cable were then connected to the corresponding terminal posts on the battery itself, starting with the negative black cable, followed by the positive red cable. With these connections completed and the breaker turned on, the charge controller will then indicate that power is being drawn from the battery. Now, the PV source circuit in this setup has both solar panels connected to a combiner box with their parallel configuration, allowing us to easily and safely provide overcurrent protection with a fuse on each positive line. This parallel configuration doubles the combined current to about 10 amps while maintaining the same voltage level of about 20 volts. And if you recall some of the aspects involved in system design, we have to make sure that the voltage and current from our solar array falls within the limits of the charge controller, which in this case are specified as 60 volts and 30 amps respectively. So from this information we can see that our solar output will stay well within the limits specified for the charge controller. But you can review our previous video for more information on how to size a solar charge controller. Now, to make the actual connections to the charge controller, we stripped the negative black and positive red outputs from the combiner box and connected them to the corresponding terminals on the solar charge controller. Both PV terminals were then tightened to secure the connection. We also connected a small 12-volt DC motor directly to the solar charge controller using a set of slip-on terminal disconnects. But once all these connections have been made, system settings can then be configured on the charge controller, including battery chemistry like AGM or lithium, charge profile, absorption, float voltage, cutoff voltage, and or low voltage disconnect. And with those connections and settings complete, as we did in a previous video, we should see the battery charging from solar as indicated on the controller's display. So, with the PV disconnect and all of the other circuit breakers closed, we have confirmed a functional system consisting of a solar array, charge controller, battery, and DC motor. So up to this point, we're harvesting power from the sun and storing it in the battery to be used at a later time.
And that's the basic system that we've built previously. But now we're going to install and integrate a 1500 watt pure sine wave inverter into the system in order to convert the energy stored in the battery into usable electricity.
For safety purposes, I'll disconnect the positive and negative cables from the battery as well as the solar array in order to prevent them from sending voltage down. And with these circuits now broken, I can then safely work on integrating the inverter into the system. To connect the inverter to the battery, we'll start by connecting the positive red cable to the positive post on the inverter and the negative black cable to its negative post. And in this case, we're using 2.0 AUG cable, but feel free to review our previous video on wire sizing for more information. In any sense, a terminal lug should be properly crimped and soldered onto the bare end of each cable. We'll then replace the washer and nut over each lug before replacing the plastic covers for additional protection. Then we'll run each wire towards the battery, but we'll fuse the positive red cable as we've done previously. It's important to install an appropriately sized external DC fuse in close proximity to the positive battery post in order to protect against fire hazard due to short circuit current along the battery cable run. And that's because batteries are unlimited current sources that can supply thousands of amperes under short circuit conditions. So if a short circuit occurs in the cable run at a point between the battery and the inverter, the section of the cable from the battery to the point of the short circuit will be fed with thousands of amperes, causing that section of the cable to overheat, melt, and/or cause a fire. We'll install a 200 amp Class T fuse and fuse holder for today's demonstration, but you may want to review our previous video on wire and fuse sizing for more information. In any case, we'll connect the positive wire from the inverter to this fuse holder, and then connect the positive wire run on the other side of the fuse, running all the way to the positive battery terminal. Next, we'll run the negative cable from the inverter all the way over to the negative battery terminal, and we'll reconnect the wires running to the charge controller along with these wires running to the inverter. The battery connections themselves may vary from the temporary use of crocodile clips like these to more robust connections using 3/8 inch wire lugs. In this case, we'll make sure that our wire lugs are flush and are maintaining firm contact with each battery post, and we'll make sure that each connection is tight and secure. And while a permanent installation would necessitate the use of conduit for many of these wire runs, in today's video we'll simply secure the wires with plastic cable ties, recognizing that our project today is only a temporary demonstration. In any sense, now that we've connected the inverter to the battery and all other components of the system, our circuit should be completed whenever the PV disconnect and all the other circuit breakers are closed again. With that done, the inverter and any connected devices or appliances should now have power. So in this case, we have solar charging the battery, and the battery powering the inverter, and the inverter powering this lamp.
Now we'll consider another example using this 3000 watt grid-tied inverter, which is designed to work with DC power optimizers, and as such it'll provide module level shutdown and monitoring capabilities.
The digital processing performed in the upper compartment of this inverter will generate a high definition sine wave at an efficiency of over 97%, but as we've seen in a previous video, most of our essential wiring and connections will be made inside the lower compartment of the system, which houses an integrated DC safety switch. And while this particular enclosure has an IP65 and NEMA 3R rating for interior or exterior installations, you may want to provide some additional shading from direct sun exposure if necessary. It really depends on your system design, the site layout, and any local requirements that you might have. With that said, no permanent mounting requirements or procedures will be considered in today's videos. Our focus today is primarily on making the essential wiring and connections within this lower compartment. And for the purpose of today's demonstration, we'll assume that all of the solar panels, racking, and equipment grounding have already been installed. We'll likewise assume that each power optimizer has been mounted to the racking system under each solar panel, where the positive and negative input from each power optimizer has been connected to the leads coming from the back of the solar panel, while the positive and negative outputs of each power optimizer have been connected in series with one another. Now, as we've done previously, we'll turn the DC safety switch to the off position and remove the cover. And if any electrical connections are already made to the inverter, then you'll want to be careful not to touch any of the components inside the enclosure. But with no connections having been made in this unit, we'll go ahead and look at the terminal blocks found on the inside. The terminal block on the lower left of this particular enclosure is specified as the DC input coming from the solar array. And as you can see, this particular terminal block is designed to accommodate up to 2 strings of solar panels, each having a positive and negative input terminal. The terminal blocks to the right, AC1 and AC2, are used for output connections to the grid from the main distribution panel and for backed up loads from the backed up loads panel respectively. Each of these terminal blocks contains 3 terminals, including line 1, line 2, and neutral. With that said, we'll only focus on the AC1 terminal block in today's video in order to run AC output lines to a main distribution panel. You may also notice the grounding bus bar centered at the bottom of the enclosure. And while there are several additional terminals found within this enclosure, we're only going to focus on the DC input, AC1 output, and the grounding bus bar in today's video. These terminals represent the essential connections for DC input from the solar array AC output to a distribution panel, and grounding.
So let's walk through these connections.
We'll start by connecting the AC power from the distribution panel to the AC1 terminal block, and we'll use a multimeter to ensure that there's no live voltage within our AC lines. And once we've confirmed that the wires are safe to work with, we'll run this 4x10 wire through a conduit entry on the right side of the enclosure. For outdoor installations, it's typically recommended to run the wire through the bottom conduit entry, but I'll pass it through the side entry in this case since I'm not actually mounting the inverter in today's video. And normally we'd install the line through a watertight gland, but we'll skip some of these steps in today's demonstration since the primary focus of today's video is on the essential wire connections to be made for this temporary system. And so we'll move right along to the actual AC connections that are to be made within the enclosure by stripping away 1 3/8 inch of wire insulation, and we'll connect the green ground wire to the grounding bus bar by inserting the stripped end into a grounding terminal and tightening its corresponding screw. Then we'll connect the hot and neutral lines to the AC1 terminal block. In this case, we'll connect the hot black conductor to the L1 terminal by inserting a screwdriver or a metal rod into its corresponding spring compression and inserting the stripped end of the black conductor into the terminal itself. This connection should be secured once the screwdriver or the rod is removed from the spring compression. Other terminal blocks may require clockwise and counterclockwise screw rotation to tighten or loosen the terminals respectively, but in any sense we'll continue these AC connections by inserting the hot red conductor into the L2 terminal, followed by the neutral or white conductor into the N terminal. We've now completed the AC connection between the inverter and the main distribution panel.
Now we'll connect this inverter to the solar array on the DC side of the system, and we'll work with 2 strings of solar panels in today's video, which can be accommodated by the 2 terminal blocks found in this particular inverter. Additional accommodations would be needed, however, if we were connecting more than 2 strings of solar panels. This would include any additional overcurrent protection as would be required by the National Electric Code.
But in this case, we'll simply run the wires coming from each string of the solar array to the inverter, and once we've confirmed the polarity and safe voltage level of these cables using a multimeter, we'll typically pass each line through a seal-tight conduit and watertight gland. Again, we'll skip the use of conduit glands and cable clips in today's video as our focus is primarily on establishing the essential AC and DC connections within the inverter. Once the lines have been passed through the conduit entry on the left side of the enclosure, we'll strip away 5/16 of an inch of insulation from the wires. We'll then connect the DC equipment grounding connector to the equipment grounding terminal block, and we'll connect the positive and negative solar wires to the corresponding DC terminals by engaging and releasing the corresponding spring clamps using a screwdriver or a metal rod just as before. Just make sure that each wire is fully inserted with no exposed copper.
Now that the AC and DC connections have been made in this inverter, we can complete any additional steps including data cable connection and/or activation.
With this inverter, for example, we could run a Cat5 or Ethernet cable from the RJ45 terminal block or the 9-pin RS485 terminal block found on the communication board, running that through the DC safety switch, through the communication gland of the inverter, and into your internet router or switch. Alternatively, you could use a wireless or a cellular connection for remote module level monitoring, but more on these topics at a later date. Any and all activation steps and pairing protocols specified by the manufacturer should then be followed for the inverter to begin monitoring the grid and producing and exporting power. Once all the wiring and activation procedures have been completed, we can replace the faceplates of the inverter and DC safety switch, being sure not to touch any of the uninsulated wires or components in the process. Again, for actual installations, we've run seal-tight flex or conduit for all of the solar lines, communication cables, and AC output, but we've left the system as it is for today's basic demonstration on wire connections. In any sense, with the main AC breaker, DC disconnect, and safety switch all turned back on, we'll now have a voltage matching that of the solar array on the DC side of the system and a grid voltage of around 240 volts on the AC side of the system.
Well, I hope this video has provided you with an understanding of how to install a solar inverter by connecting the DC and AC wiring. In upcoming videos, we'll consider other aspects of solar electric systems, including electrical grounding and more. You can subscribe to this channel to stay connected on upcoming episodes of this Solar Clips video series, but in the meantime, please visit our website for more information on solar, photovoltaics, and other energy-related topics.